Hi everybody, this is section 3 from Module 1 for Math 026 for Hartford Community College. And in this section we are going to look at the product and quotient rule of radicals and then also simplifying radicals. The first thing we're going to look at is the product rule of radicals. And the product rule of radicals states, you can see it right here, that if you have two radicals that have the same index, you can multiply the values, the radicands, and combine it into one single radical. But the key here is it must have the same index. So your radicals, in order to multiply them, must have the same index. Then we also have the product rule, or the quotient rule of radicals. And that says that if you have a problem where you have two radicals and you're dividing one by the other and they have the same index, you can, if you want, combine them into one single radical and simplify it that way. Or if it's one single radical, you can break it up into two to help you simplify. Whatever works best to help you simplify. We're going to take a look at some examples here. Our first one that we have for A is the cubed root of 6x times the cubed root of 3x. And here, because my indexes are the same, I can multiply these together and combine them under one single radical. So my answer is going to be the cubed root of 6 times 3 is 18. And x times x will give me x squared because you add those exponents. All right, next for B, we have the square root of 18 times the square root of 2. So I'm going to multiply that together, and 18 times 2 is going to give me 36. So we have the square root of 36, and that is a perfect square, so I can simplify it. So the square root of 36 will equal 6. And then for letter C, the last one on this page, we have the fourth root of 27, a cubed b to the 8th power, times the fourth root of 3ab. So again, both of the indexes are the same, so I can multiply it together. And I'm going to end up with the fourth root of 27 times 3, I am going to use my calculator real quick, is 81. So we have the fourth root of 81. And then a to the third times a will give me a to the fourth, because we add those exponents. B to the 8th times b will give me b to the 9th power. Now, if we are looking at that, I do have a couple of values that could be simplified here that are perfect squares. We'll talk about the b to the 9th in the next section, so I'm going to leave that as is right now. But I know the fourth root of 81 is 3, and the fourth root of a to the fourth, 4 goes into 4 one whole time. Now, right now, all you guys know would be to leave it like this, the fourth root of b to the 9th. But I am going to tell you the actual answer, and then we're going to talk about it in the next section so you can kind of see how we got that. When we're simplifying, 4 does not divide evenly into 9, but 4 goes into 9 2 times, because 4 times 2 is 8. And then you have a remainder of 1. So if I were to write this simplified answer, it would be 3a, b to the 2nd power, and then times the fourth root of b. And again, we'll talk about more about that in the next section, simplifying radicals. All right, now we're going to look at some of our division problems. And we are going to start off. So for the first one, if you look at it, we have the square root of 125x cubed divided by the square root of 5x. But right now, they're not perfect squares, so I really can't do anything with it. But if I were to write it as one radical, so if I make one large radical, And I have 125x cubed divided by 5x. Now, because that fraction is all under one radical, I can simplify that fraction and then potentially simplify anything that results from it. So I know 125 divided by 5 is going to give me 25. So again, we're not taking away the radical yet, but if I take and I divide 5 into 125, it gives me the whole number 25. And x cubed divided by x would give me x squared. And now that I'm looking at that, because I did have that one fraction that I could simplify, I know that the square root of 25 is 5, and the square root of x squared is x. So I get a final answer of 5x. Right, next, we have the cubed root of 56p to the 19th power q to the 25th divided by the cubed root of 7p to the 4th q to the 7th. So again, really can't do anything with it as it stands, but I can rewrite it as one large fraction. So I'm going to do the cubed root of 50, let me erase that, that didn't come out very good. 56p to the 19th q to the 25th divided by 7p to the 4th q to the 7th. And I'm going to go ahead and simplify that. And again, I haven't taken the cubed root of anything, so it's still going to remain under the radical. But I do know that 56 divided by 7 is going to equal 8. And then p to the 19th divided by p to the 4th will end up being p to the 15th because we subtract those exponents. Q to the 25th divided by q to the 7th. When I subtract 25 minus 7, I end up with q to the 18th power. And now I can take the cubed root of these values. I know the cubed root of 8 is 2. 3 goes into 15 5 times, so that's going to make it p to the 5th. And then 3 goes into 18 6 times, so it will be q to the 6th. So my final answer here is 2 p to the 5th q to the 6th. All right, now for the next one, we're looking at the 4th root of 16 over 81. And right now, I really can't do any simplifying as it stands, but this is a case where if it's one single fraction, see if you can break it up. So now I'm going to look at it as the 4th root of 16 over the 4th root of 81. And I do know that the 4th root of 16 is 2, and the 4th root of 81 is 3. So I can simplify it and make it into 2/3. All right, so here's another example where we can split it up into two separate radicals. So I'm going to have the cubed root of negative 126 over the cubed root of 125. Now, before we could simplify both, but this one, I don't know the cubed root of 126, but I do know the cubed root of 125 is 5. So I can simplify part of the radical by splitting it up, just not all of it, and that's okay. But if you can simplify some by if you can simplify some of it by breaking it up, that's the best thing to do. All right, next we have h, and it is got that negative symbol on the outside, so we want the opposite of the 5th root of x squared, which I can't do anything with, so I'm going to leave it as is, and the 5th root of 32 y to the 10th. Now, that negative can, it's outside the radical. It's right here. It's part of the fraction. When you put the radical or the negative symbol, you can be with the numerator, with the fraction bar, or the denominator. It makes the whole fraction negative. So I'm going to leave it at the top. I can't do anything with the top, so I'm going to leave it as the opposite, or negative 5th root of x squared. But on the bottom, I do know the 5th root of 32 is 2, and 5 goes into 10 2 times. So 5 divided into 10 is 2, so we have 2y squared on the bottom. And that's going to be simplified. All right, and then for I, again, I'm going to split it up because I can't really simplify the fraction as it is. But if I do the square root of 64 a to the 9th over the square root of 81 b to the 10th, we know the square root of 64 is 8. And a to the 9th, this is another one where it's not a perfect radical, but I do know that 2 does go into 9 4 times. So I'm going to pull out a to the 4th. And then I do have a remainder of 1. And again, we're going to look at that more in the next section. But what I did is when I simplified that, I had the square root of a to the 9th power. I know if we look at the division here, 2 goes into 9 4 whole times. 2 times 4 is 8. When I subtract, I have a remainder. When you do this and you subtract or have a remainder left over, that always stays under the radical. What we're saying is I can pull out 4 groups of 2 from that 9. I just have 1 left over. So we're going to leave it like this. And then on the bottom, the square root of 81 is 9. And if we take 2 and again divide it into 10, we come out with b to the 5th power. And that would be it for that problem. And we're done simplifying as much as we can. All right, so the next thing we're going to do in this section, the last part of this section, is going to deal with simplifying radical expressions. We talked about in the very first section how we have perfect roots or perfect squares, perfect cubes where our answers are whole numbers. And then we have problems where it is not a perfect cubed root or square root. And our answer is an irrational number. So if they ask you to approximate your answer, you can write it as a decimal. But if they want the exact answer, you want to simplify that radical as much as you can. Kind of think of it like simplifying a fraction. If there is a perfect square in that radical, you want to pull it out and leave only the values that are not perfect squares, perfect cubes, or perfect nth roots. So you want to split it up. And if you look at your notes, you'll see you have a couple examples that you can look at, and then we're going to work through the examples that are listed as well. So our first one is the square root of 12. It is not a perfect square. I can't think of 2 numbers, whole numbers, that I can multiply together to get 12 that are exactly the same. But when I think about my factors of 12, and that is, what do you multiply together to get 12? I know I can do 1 and 12, which doesn't help me. There's 2 and 6, or there's 3 and 4. Now, this is a square root, so I want you to look through these pairs of factors. Can you see one of those pairs that has a perfect square in it? And hopefully you're saying, oh, look, there's 3 and 4. And 4 is a perfect square root. So if I take the square root of 12 and break it up, and I make it square root of 3 times the square root of 4, I know that I can't simplify the square root of 3, but the square root of 4 is 2, and then we'll leave the square root of 3. So the square root of 12 in simplest radical form is 2 square root 3. And we always write the whole number first and then the radical. All right, next let's look at the square root of 72. So again, look at your factors of 72. And I know for 72, I have 1 and 72. Or I could do 36 and 2. What else? 72 divided by 3 is 3 and 24. And we could do 4 and 18. And let's see here, 72 divided by 6 and 12. Or 8 and 9. So now, if I'm looking at these pairs, I want to find pairs with perfect squares. 1 and 72 I know does not. 2 and 36. I know 36 is a perfect square. Let's just go through the rest and look at them. 3 and 24, no. 4 and 18. 4 is a perfect square, so we could use that one if we wanted to. It's too quick to cross it out. 4 and 18. So that's another one we could use. 6 and 12, no. 8 and 9. 9 is a perfect square. Now, you're saying, well, we have all these different choices. We do. Really, what you want to do is choose the largest perfect square so that you don't have to break it down multiple times. If I did 4 and 18, I get 2 from 4. But then 18, I also know I could do 9 times 2, so I'd have to break it down a little bit more. And here, 9, the square root of 9 is 3, but then I have to break down 8 because that's 4 times 2. So we're going to go with 36 times 2. So we have the square root of 36 times the square root of 2, and the square root of 36 is 6, and then we have our 2. Now, if you chose to break it down a little bit differently, that just means, again, like I said, you'd have to break down a number more than once. All right, so now we are looking at the cubed root of 72. We want to simplify that. So again, if we think about our 72, we know, and we looked at the factors, 1 and 72, 36 and 2. It was 3 and 24, 4 and 18, 6 and 12, and then 8 and 9. Okay. Now, we are looking at cubed roots now, so we need perfect cubes, not perfect squares. So 36 and 2 is not going to work this time. 24 and 3 are not perfect cubes. And again, this is where make that little list on the side, or if you know it, like 2 to the 3rd power we know is 8. 3 to the 3rd power is 27. And look for those values. I know 18 and 4 won't work, 12 and 6 won't work, but here, 9 and 8, that will work because 8 is a perfect cube. So when I go to break it down, I'll have the cubed root of 8 times the cubed root of 9. The cubed root of 8 is 2. And then we can't do anything with the cubed root of 9, so we'll just leave it. So my answer is 2 cubed root of 9. All right, next we have the 4th root of 64. So we want to look at our factors of 64. So we have 64, 1 and 64, which again won't help me. 2 and 32. 3 does not go into 64. 4 goes into 64 16 times, so 4 and 16. And then I believe we just have 8 times 8. Now we need 4th roots here. So again, I'm going to look at I'm going to start with like 2 to the 4th power, which I know 2 to the 4th power is 16. 3 to the 4th power is 81, so I know that's going to be too big. So, but I do have in my 64, I have a 16. We have 4 times 16. So we're going to break it down. We're going to make it the 4th root of 16 times the 4th root of 4. The 4th root of 16 is 2, and then it'll be times the 4th root of 4. So now we have 2 4th root 4 as our simplified version of the 4th root of 64. All right, and for our last one, I'm going to erase just a little bit over here so we have a little more space. We are going to look at variables now. And we kind of already have started this. Remember, and I'm going to write it, it's the square root of x to the 7th power, y to the 12th. And really what you want to do is you want to figure out, well, how many groups of 2 can I pull out for the x's and for the y's? Sometimes you may have a remainder, and that stays under the radical. Again, do this with your division. So I know that if I take and I divide 2 into 7, I'm just going to do it over here. So 2 into 7. 2 goes into 7 3 times. 2 times 3 is 6. So when I subtract, I have 1 left over. Or think of it as a remainder of 1. So that's telling me I can pull out 3 groups of 2 from 2x to the 7th. So I'm going to have x to the 3rd power. So think this is going to be your exponent. This is going to tell you how many x's remain under the radical, the remainder. I'm going to leave a little space here, put my x. Now, y. 2 goes into 12 6 times, and there is no remainder, so there's nothing left under the radical, so we would just have y to the 6th power times the square root of x, because that's our only remainder. So our answer there would be x to the 3rd power, y to the 6th, times the square root of x. All right, so now here for f, we are going to simplify the square root of 48, a to the 16th, b to the 10th. So we're going to start off and break it down. Really, you can look at it in separate parts. I'm going to look at 48 first. So I'm going to look at my factors of 48, which are 1 and 48, which aren't going to help me, but 2 and 24, 3 and 16, and then 4 and 12. And I'm going to stop there because I see the first one that I can use, the 3 and 16. So I'm going to break my 48 into the square root of 16, not very good, times the square root of 3. And that's going to give me 4 square root 3. And I'm going to leave a little space there because I got to put the rest of it on. Now, next, we're going to look at our variables. So we're going to focus on, we have the square root of a to the 16th, b to the 10th. So if I put my 2 in there, 2 goes into 16 8 times, and it goes in evenly. So that would give me a to the 8th. And then let me move this over a little. I didn't leave enough space. 2 goes into 10 2 or 5 whole times, so it would be b to the 10th. And then we would just have our square root 3. So when we simplify, we get 4 a to the 8th, b to the, not 10th, but to the 5th, because it goes in 5 times, times the square root of 3. All right, next we are going to break down 500. Again, square root, so I'm going to look at 500. Now, here, you can probably start thinking about your perfect squares. There's a lot of factors to 500, but I do know 100 times 5, because 100 is a perfect square. So I can break it down to the square root of 100 times the square root of 5. So that will give me 10. And then I'll leave a little space. We got the square root of 5 here. Now let's look at our variables. We have an f here. It's the only variable. It has an exponent of 1, the only f. So we can't do anything with it. So I'm going to just rewrite it under the radical. I have g to the 2nd power. So if I divide 2 into 2, I get 1 whole number. So I can pull out 1 pair of g's. And then h to the 3rd power. So if I take and I divide 2 into 3, it goes in 1 whole time, and you have a remainder of 1. So that means I'm going to have 1 h on the outside and 1 h on the inside, because I pulled out 1 group of 2, and then I have 1 left over. So again, 1 group of 2, that goes on the outside. Your whole number, your remainder is how many h's you would have on the inside. So our final answer here would be 10gh square root 5 fh. All right, and our last one on this slide is the cubed root of 16 x to the 9th, y to the 14th. So we talked about cubed roots before. 16, I know right away I can do 2 and 8 or 4 and 4, but because I want a perfect cubed root, I'm going to do 2 and 8. So that'll be broken down as the cubed root of 8 times the cubed root of 2. The cubed root of 8 is 2, and then I'm going to leave a little space, put the cubed root of 2 here. Now, we are looking at the cubed root of x to the 9th power next. 3 goes into 9 3 whole times with 0 remainder, so I'm going to move x to the 3rd out here. And then we are doing the cubed root of y to the 14th. And 3 goes into 14 4 times, 4 whole times. And there is a remainder of 2. So that means I will have y to the 4th on the outside. My remainder is 2, so I'll have y to the 2nd power on the inside. So my final answer is 2, x cubed, y to the 4th, times the cubed root of 2y to the 2nd power. All right, we have our last two that we're going to look at. And next we're going to do the cubed root of 128, a to the 22nd, b to the 23rd. So let's see, we're going to break down 128. And I do know that I can do, we need a cubed root. I can do 2 times 64 to get 128. And 64 is a perfect square, but it's also a perfect cube for 4. So I'm going to break this down into the cubed root of 64 times the cubed root of 2. So the cubed root of 64 is 4, and then we'll leave our cubed root of 2 right here. All right, next we have a to the 22nd. So if I take 3 and divide it into 22, I know that 3 goes into 22 7 times. 3 times 7 is 21, so that leaves me with a remainder of 1. So that means I can pull out 7 groups of 3a's. So a to the 7th. And I have 1a left over on the inside because my remainder was 1. Next we have b to the 23rd. So I'm going to take 3 and divide it into 23. 3 goes into 23 7 times. And we have a remainder of 2. So that would give me b to the 7th again. And we had a remainder of 2, so b to the 2nd power on the inside. Sorry, that's not a very good 2. Let me fix that. So our final answer is 4 a to the 7th, b to the 7th, times the cubed root of 2ab squared. All right, our last one is the 4th root of 162, s to the 20th, t to the 30th. And here, sometimes it's a little easier if we look at our 4th roots. Like if I do 2 to the 4th power, so if I know 2 to the 4th power, I know that is 16. 3 to the 4th power is 81. 4 to the 4th power is, I gotta figure that out myself. Hold on. 4 to the 4th power is 256. So I know that's too big. So what I'm going to do is to see if there's any perfect roots in there when it gets a little bit bigger. I'm going to take the 162 and divide it by 81 because that I know is a perfect 4th root, and I get 2. So that means I can break down the 162 into the 4th root of 81 times the 4th root of 2. The 4th root of 81 is 3. And then we have our 4th root of 2 that we can't do anything with, so we're going to leave it there. Next, 4 goes into 20 5 times, so I'm going to have s to the 5th power. And 4 goes into 30 7 times. 4 times 7 is 28. So then we have a remainder of 2. So now we're going to have t to the 7th power on the outside, because it went in 7 whole times, and then t to the 2nd on the inside, because that was my remainder. So our final answer is 3 s to the 5th power t to the 7th times the 4th root of 2t squared. And that is it for the end of part 3.